Lead is a chemical element in the carbon group with symbol Pb and atomic number 82. It is a soft, malleable and heavy post-transition metal. Freshly cut, solid lead has a bluish-white color that soon tarnishes to a dull grayish color when exposed to air. The liquid metal has shiny chrome silver luster. Lead has the highest atomic number of any non-radioactive element, although the next higher element, bismuth, has one isotope with a half-life that is long enough to be considered stable. Lead's 4 stable isotopes each have 82 protons, a magic number in the nuclear shell model of atomic nuclei. The isotope Lead-208 also has 126 neutrons, another magic number, and is hence double magic, a property that grants it enhanced stability. Lead-208 is the heaviest known stable nuclide. Lead is used in building construction, lead-acid batteries, bullets and shot weights, as part of solders, pewters, fusible alloys, and as a radiation shield. If ingested or inhaled, lead and its compounds are poisonous to animals and humans. Lead is a neurotoxin that accumulates both in soft tissues and the bones, damaging the nervous system and causing brain disorders. Excessive lead also causes blood disorders in mammals. Lead poisoning has been documented since ancient Rome, ancient Greece, and ancient China. Physical characteristics. Bulk properties. Lead is a bright silvery metal with a very slight shade of blue in a dry atmosphere. It tarnishes on contact with air, forming a complex mixture of compounds whose color and composition depend on conditions, sometimes with significant amounts of carbonates and hydroxycarbonates. Lead's characteristic properties include high density, softness, ductility, malleability, poor electrical conductivity compared to other metals, high resistance to corrosion, and ability to react with organic chemicals. Various traces of other metals significantly change its properties. Adding small amounts of antimony or copper increases the lead alloy's hardness and improves resistance to sulfuric acid corrosion. Some other metals, such as cadmium, tin, and tellurium, improve hardness and fight metal fatigue. Sodium and calcium also have this ability, but they reduce the alloy's chemical stability. Finally, zinc and bismuth simply impair the corrosion resistance. Adding small amounts of lead improved the ductility of steel, but lead impurities mostly worsen the quality of industrial materials. Lead has only one common allotrope, which is face-centered cubic, with the length of an edge of a unit cell being 349 pm. Unlike the other elements in its group, it does not have a diamond cubic allotrope. At 327.5 degrees Celsius, lead melts. The melting point exceeds that of tin, but is significantly below that of germanium. The boiling point of lead is 1749 degrees Celsius below those of both tin and germanium. Densities increase down the group. The values of germanium and tin are significantly below that of lead, 11.32 grams cm-3. Isotopes. Lead has 4 observationally stable isotopes: Lead-204, Lead-206, Lead-207, and Lead-208. The relative multitude of its stable isotopes relies on the fact that lead's atomic number of 82 is even with its high atomic number. Lead is the second heaviest element that occurs naturally in the form of isotopes that could be treated as stable for any practical applications. Bismuth has a higher atomic number of 83, but its only primordial isotope was found in 2003 to be actually very slightly radioactive. The four stable isotopes of lead could theoretically undergo alpha decay to isotopes of mercury with release of energy as well, but this has not been observed for any of them. Accordingly, the predicted half-lives are extremely long, ranging up to over 10,100 years. As such, lead is often quoted as the heaviest stable element. Three of these isotopes also found in three of the four major decay chains: Lead-206, Lead-207, and Lead-208 are the final decay products of uranium-238, uranium-235, and thorium-232, respectively. The decay chains are called the uranium series, actinium series, and thorium series, respectively, since the amounts of them in nature depend also on the presence of other elements. The isotopic composition of natural lead varies between samples. In particular, the relative amount of Lead-206 may vary between 20.84% and 27.78%, and the relative amount of Lead-208 may vary between 52.4% in normal samples to 90% in thorium ores. As time passes, relative amounts of Lead-206 and Lead-207 to that of Lead-204 increase, since the former two are supplemented by radioactive decay of heavier elements and the latter is not. This allows for lead-lead dating. Analogously, as uranium decays into lead, the relative amounts change. This allows for uranium-lead dating. Apart from the stable isotopes, which make up almost all of lead that exists naturally, there are trace quantities of a few radioactive isotopes. One of them is Lead-210. Although it has a half-life of 22.3 years, a period too short to allow any primordial Lead-210 to still exist, some small non-primordial quantities of it occur in nature, because Lead-210 is found in the uranium series. Thus, even though it constantly decays away, its amount is also constantly regenerated by decay of its parent, polonium-214, which, while also constantly decaying, is also supplied by decay of its parent, and so on, all the way up to original uranium-238, which has been present for billions of years on Earth. Lead-210 is particularly well known for helping to identify ages of samples containing it, which is performed by measuring Lead-210 to Lead-206 ratios. Lead-214 is also present in the decay chain of natural uranium-238. Lead-212 is present in that of natural thorium-232, and Lead-211 is present in that of natural uranium-235. Therefore, traces of all three of these isotopes exist naturally as well. Lastly, very minute traces of Lead-209 are also present from the cluster decay of radium-223, one of the daughter products of natural uranium-235. Hence, natural lead consists of not only the four stable isotopes, but also minute traces of another 5 short-lived radioisotopes. In total, 38 isotopes of lead have been synthesized, those with mass numbers of 178 to 215. Lead-205 is the most stable radioisotope of lead, with a half-life of around 1.5 times 107 years. The second most stable radioisotope is the synthetic Lead-202, which has a half-life of about 53,000 years, longer than any of the natural trace radioisotopes. Additionally, 47 nuclear isomers, corresponding to 24 lead isotopes, have been characterized. The longest-lived isomer is Lead-204M2. Chemical characteristics. A lead atom has 82 electrons, arranged in an electronic configuration of 4f145d. 106 is 26p2. The first and second ionization energies required to remove an electron from a neutral atom and an electron from a resulting singly charged ion of lead combined are close to those of tin, its upper group 14 neighbor. This proximity is caused by the 4f shell. No f shell is present in previous group 14 elements atoms, and the thereby following lanthanide contraction. However, the first 4 ionization energies of lead combined exceed those of tin, opposite to what the periodic trends would predict. For that reason, unlike tin, lead is reluctant to form the +4 oxidation state in inorganic compounds. Such unusual behavior is rationalized by relativistic effects, which are increasingly stronger closer to the bottom of the periodic table. One of such effects is the spin-orbit interaction, particularly the inert pair effect, which stabilizes the 6s orbital. The inert pair effect in lead comes from the great difference in electronegativity between lead and the anions, which results in positive charge on lead and then leads to a stronger contraction of the 6s orbital than the 6p orbital, making the 6s orbital rather inert. The spin-orbit interaction not only stabilizes the 6s electron levels, but also 2 of the 6p levels, and lead has just 2 6p electrons. This effect takes part in making lead slightly less reactive chemically. The figures for electrode potential show that lead is only slightly easier to oxidize than hydrogen. Lead thus can dissolve in acids, but this is often impossible due to specific problems. Electronegativity, although often thought to be constant for each element, is a variable property. Lead shows a higher electronegativity difference between values for lead and lead 1.87 and 2.33 accordingly. This marks the reversal of the trend of stability of the +4 oxidation state in group 14 down the group from increasing to decreasing. Tin, for comparison, has electronegativities of 1.80 and 1.96. Reactivity. Powdered lead burns with a bluish-white flame. As with many metals, finely divided powdered lead exhibits pyrophoricity. Bulk lead released to the air forms a protective layer of insoluble lead oxide, which covers the metal from undergoing further reactions. Other insoluble compounds, such as sulfate chloride, may form the protective layer if lead is exposed to a different chemical environment. Fluorine reacts with lead at room temperature, forming lead fluoride. The reaction with chlorine is similar, although it requires heating. The chloride layer diminishes the reactivity of the elements. Molten lead reacts with all the chalcogens. Presence of carbonates or sulfates results in the formation of insoluble lead salts, which protect the metal from corrosion. So does carbon dioxide, as the insoluble lead carbonate is formed. However, an excess of the gas leads to the formation of the soluble bicarbonate, which makes the use of lead pipes dangerous. Water in the presence of oxygen attacks lead to start an accelerating reaction. Lead also dissolves in quite concentrated alkalis because of the amphoteric character and solubility of plumbites. The metal is normally not attacked by sulfuric acid. However, concentrated acid does dissolve lead thanks to complexation. Lead does react with hydrochloric acid, albeit slowly, and nitric acid, quite actively, to form nitrogen oxides and lead nitrate. Organic acids, such as acetic acid, also dissolves lead, but this reaction requires oxygen as well. Inorganic compounds. In a vast majority of its compounds, lead occurs in oxidation states +2 or +4. Lead compounds are normally ionic, but lead compounds are often covalent. Even the strongest oxidizing agents among the elements, oxygen and fluorine, oxidize lead to only lead initially. Lead most inorganic compounds that lead forms are lead compounds. This includes binary compounds. Lead forms such compounds with many nonmetals but not with all of them, as for example there is no known lead carbide. Even though most lead compounds are ionic, they are not as ionic as those of many other metals. In particular, many lead compounds are water-insoluble. In solution, lead ions are colorless, but under specific conditions, lead is capable of changing its color. Unlike tin ions, these do not react as reducing agents in solution. Lead monoxide exists in two allotropes, red alpha-lead-2 oxide and yellow beta-lead-2 oxide, the latter being stable only from around 488 degrees Celsius. It is the most commonly applicable compound of lead. However, its hydroxide counterpart, lead hydroxide, is not capable of existence outside solutions. In solution, it is known to form anions, plumbites. Lead commonly reacts with the heavier chalcogens. Lead sulfide can only be dissolved in strong acids. It is a semiconductor, a photoconductor, and an extremely sensitive infrared radiation detector. A mixture of the monoxide and the monosulfide when heated forms the metal. The other two chalcogenides are photoconducting as well. Lead dihalides are known and well characterized. This refers to not only the binary halides, but also mixed ones, such as PbFCl, etc. The difluoride is the first ionically conducting compound to have been discovered. The other dihalides decompose on exposure to ultraviolet visible light, especially notably for the diiodide. There are anion counterparts for the heavier 3-dihalides, such as lead 4-chloride-6. Many pseudo-halides are also known. Few lead compounds are known. Inorganic lead compounds are typically strong oxidants, or exist only in highly acidic solutions. Lead oxide gives a mixed oxide on further oxidation, Pb3O4. It is described as lead oxide, or structurally 2-lead-2 oxide lead-2 oxide 2, and is the best-known mixed valence lead compound. Lead dioxide is a strong oxidizing agent, capable of oxidizing hydrochloric acid. Like lead monoxide, lead dioxide is capable of forming anions, plumbates. Lead tetrafluoride, a yellow crystalline powder, is stable, but less stable than the difluoride. Lead tetrachloride decomposes at room temperature. Lead tetrabromide is less stable still, and the existence of lead tetraiodide is questionable. Lead disulfide, like the monosulfide, is a semiconductor. Lead selenide is also known. Other oxidation states. A few compounds exist in oxidation states other than +2 and +4, but they do not have a great impact on lead chemistry from either theoretical or industrial perspective. Lead may be obtained under specific conditions as an intermediate between lead and lead, in larger organolead complexes rather than by itself. This oxidation state is not specifically stable, as the lead ion is a radical. The same applies for lead, which can also be found in such species. Negative oxidation states can occur as Zintal phases, as either free lead ions, for example, in Ba. 2 petabits with lead formerly being lead, or cluster ions, for example, in a Pb5-2 ion, where 2 lead atoms are lead and 3 are lead. This illustrates lead's proclivity towards catenation, an ability shared with tin. Organolead lead can form long singly or multiply bonded chains and so shares some covalent chemistry with its lighter homologue carbon. This tendency is much lower for lead because the Pb-Pb bond energy is much lower than for the C-C bond. Lead atoms can build metal-metal bonds of order up to 3. Lead also forms covalent bonds with carbon to produce organolead compounds similar to but generally less stable than typical organic compounds. The simplest lead analog of an organic compound is plumbane, the lead analog of methane. It is unstable against heat, decaying in heated tubes, and thermodynamically, in general, little is known about chemistry of plumbane, as it is so unstable. A lead analog of the next alkane, ethane, is not known. Two simple plumbane derivatives, tetramethylead and tetraethylead, are the best-known organolead compounds. These compounds are relatively unstable against heating. Tetraethylead starts to decompose at only 100 degrees Celsius, as well as sunlight or ultraviolet light. General oxidizing nature of organolead compounds finds its use in chemistry. Tetraethylead is produced in larger quantities than any other organometallic compound. Lead tetraacetate is an important laboratory reagent for oxidation in organic chemistry. Other organolead compounds, including homologs of the said compounds, are still less chemically stable. Lead readily forms an equimolar alloy with sodium metal that reacts with alkyl halides to form organometallic compounds of lead such as tetraethylead. Plumbane may be obtained in a reaction between metallic lead and atomic hydrogen. Atoms of chlorine or bromine displace alkyls in tetramethylead and tetraethylead. Hydrogen chloride, a byproduct of the previous reaction, further reacts with the halogenated molecules to complete mineralization, a chemical reaction or a series of reactions transforming an organic compound into an inorganic one of the original compounds, yielding lead dichloride. Origin and occurrence. In space primordial lead, the isotopes Lead-204, Lead-206, Lead-207, and Lead-208 was created by the S process and the R process. The letter S stands for slow or slow neutron capture, and the letter R stands for rapid neutron capture. In the S process, another capture takes the long time, centuries or millennia, while the R process takes only tens of seconds to result in a heavy nuclide of lead's mass. In the S process, a nucleus in a star captures another slow neutron, and if the resulting nucleus is unstable, it typically undergoes a beta decay to become an element of the next atomic number. Lead-204 is created from short-lived thallium-204. On capturing another neutron, it becomes Lead-205, which, while unstable, is stable enough to generally last longer than a capture takes. Further captures result in Lead-206, Lead-207, and Lead-208. On capturing another neutron, Lead-208 becomes Lead-209, which quickly decays into bismuth-209, which on capturing another neutron becomes bismuth-210, which either undergoes an alpha decay to result in thallium-206, which would beta decay into Lead-206, or a beta decay to yield polonium-210, which would inevitably alpha decay into Lead-206 as well, and the cycle ends at Lead-206, Lead-207, Lead-208, and bismuth-209. As a result, relative abundances of the three have stable lead isotopes multiplied by a cycling factor, which depends on the conditions of the process. Furthermore, Lead-208 and bismuth-209 have a very low cross-section towards neutron capture because of the closed neutron shell at neutron number 126. Lead and bismuth are thus very common in stars, in which nucleosynthesis mostly happens through the S process. Apart from the S process, the latter three isotopes have been synthesized as a result of the R process. The R process happens in mediums of great electron density. In such conditions, beta decay is blocked, because the high electron density fills all available free electron states up to a Fermi energy which is greater than the energy of nuclear beta decay. But nuclear capture of those free neutrons can still occur, and it causes neutron enrichment of matter. This results in extremely high density of free neutrons which cannot decay, and, correspondingly, a large neutron flux and high temperatures, which is the reason why neutron capture occurs much faster than beta decay. However, the R process does not directly form as much lead as the S process, because neutron-rich nuclei with mass numbers chapters 206 to 208 that would decay to lead are not magic, unlike those that reach the closed neutron shell at neutron number 126 and decay to the platinum group metals around mass number 194. This effect is nevertheless masked, because these lead isotopes are also located at the end of three major decay chains. They are created by the decay of the heavier elements, which are also created by the R process. Nuclides with mass numbers between 210 and 231 inclusive, as well as 233 and 234, quickly undergo alpha and beta decay to stable lead and bismuth isotopes. However, nuclides with mass numbers chapter 232 as well as 235 and above soon decay to the extremely long-lived isotopes of thorium and uranium, which decay very slowly to lead. Hence, the amount of lead in the universe is still slowly increasing. The isotopes at the end of the chains make up around 98.02% lead in the universe, with non-radiogenic lead 204 making up slightly less than 2%. Lead is not an abundant element in general. Its per particle abundance in the universe is 0.06 ppb. Still, it is an order of magnitude more abundant than mercury, and further exceeds those of most other elements of similar atomic numbers. After element 40, no element is at least twofold as abundant as lead, and there is no element as abundant as lead starting after element 56. Lead is 3 times as abundant as platinum, 10 times as mercury, and 20 times as gold. Per mass, lead's abundance is 10 ppb. The difference between the per mass and per particle abundances is justified by mass difference between lead isotopes, and the most common elements. The most common nuclide in the universe, hydrogen-1, has a mass of approximately 1 atomic mass unit, while those of lead isotopes have masses of over 200 atomic mass units. On Earth, since lead commonly reacts with sulfur, it is classified as a chalcophile using the Goldschmidt classification. Lead is likely to form minerals that do not sink into the core but that stay above on Earth in its crust, even though without sinking deep into it. Lead's abundance in the Earth's crust is 16 ppm. This results in a great availability of lead minerals and easy extraction of the metal. For this reason, the mineral form of its sulfide, galena, has been known for millennia, as was the metal itself. Lead's pronounced chalcophilic character is close to those of zinc and copper. As such, it is usually found in or and extracted together with these metals. Metallic lead does occur in nature, but it is rare. As a result of lead's chemistry, it occurs in primary minerals exclusively as lead, unlike tin, which always occurs as tin. Lead deposits can be hydrothermal vein impregnation, and replacement deposits, volcanogenic sedimentary deposits, and hydrothermal marine sedimentary deposits. World resources of lead exceed 2 billion tons. Massive resources are located in Australia, China, Ireland, Mexico, Peru, Portugal, Russia, and the United States. World reserves, resources ready to be mined for which that would be economically feasible, totaled 89 million tons in 2015, of which Australia had 35 million, China had 15.8 million, and Russia had 9.2 million. The main lead mineral is galena. Galena is mostly found with other minerals, mostly zinc ores. Most other lead minerals are normally related to galena in some way. For example, boulangerite Pb5Sb 4S11 is a mixed sulfide derived from galena. Anglesite PbSO4 is a product of galena oxidation. Cerussite, a white lead, or PbCO3, is a decomposition product of galena. Zinc, copper, arsenic, tin, antimony, silver, gold, and bismuth are common impurities in lead minerals. Typical background concentrations of lead do not exceed 0.1 micrograms per cubic meter in the atmosphere, 100 milligrams per kilogram in soil, 5 micrograms L in fresh water and seawater.